Good morning, everybody. Welcome to the third session of this module on cement production, composition, and chemistry. So, in the first lecture, we had an idea about how cement is produced, what are the different raw materials, how they are selected, and how they interact in the process of cement manufacture to result in the kind of Portland cement that we use for concrete production today. In the second lesson, we tried to understand what is the compound composition of cement and how this compound composition is actually formed when the cement production happens. What are the different categories of compounds, silicates and aluminates, and what are the different stoichiometries that are possible within these compounds, how many polymorphic forms exist within these compounds, and how these compounds are actually graded in different international standards to produce different types of cement. So, we had an overview of the different standards, especially ASTM, BIS and EN standards. So, today we are going to take it a little bit further and get to the real relevance of the topic, try to understand how these compounds interact when cement hydrates or reacts with water. So, what are the different reactions that are involved in this system, which ultimately leads to the performance of cement as we know in concrete, and how it actually governs the overall properties of the concrete. Okay. So, today our emphasis will be on cement chemistry, but anyway, so our emphasis today is going to be on cement chemistry. So, first of all, what you need to understand about cement chemistry is the reaction of cement with water. As you all know, this reaction is called hydration, okay, and we all know that this hydration reaction is also exothermic. That means it releases heat, and the heat that is released is also known as heat of hydration. Okay, and the rate of heat evolution is generally faster when the cement reaction happens much quicker, and the heat evolved in a cementitious reaction depends on the heat of hydration of the individual compounds C3S, C2S, C3A and C4AF, and also on the clinker morphology. I mean, we are not just talking about how many fractions, how much amount of these compounds is actually present, but in what particle sizes are they present inside the cement, and those particle sizes of these compounds are actually governed by the way that cement manufacture happens. And as I said earlier, the civil engineer does not really have much of a choice with respect to the type of morphology or the type of compound composition that you ultimately result with. You get what is typically branded as an ordinary Portland cement, but there are so many other factors within this which actually control the way that the cement really hydrates. Okay. So, now let us look a little bit further at this heat of hydration and what are the different compounds as far as heat of hydration is concerned, how do they rank in terms of heats of hydration. So, if you look at the heat evolution amongst the cementitious compounds, the highest heat evolution happens with the C3A. Okay. Please remember earlier that we talked about the fact that in cement manufacturing process, we add gypsum as an ingredient in the final stages to ensure that the cement sets and hardens at a normal rate. In the absence of gypsum, cement sets very rapidly and we call that as flash setting. Okay. And that generally happens because our C3A, that is the most reactive compound in the cement, reacts immediately with water to form an aluminate hydrate. I will talk about these reactions further, but again, because of this very quick propensity to react with the C3A, its heat of hydration is also the highest. If you look in this table here, C3A has about 867 joules per gram of heat that it produces. The next in line is C3S, which is about 502. So, C3S, I told you earlier, modern Portland cement has high content of C3S because this is the primary product that gives us early strength, and because it gives early strength, it reacts faster, and because it is reacting faster, it is also possessing a high heat of hydration. After C3S is C4AF, and then finally the least heat of hydration is C2S. Please remember, we had talked about general principles of cement classification. I said that when you want to lower the heat of hydration, you need to increase the C2S content and reduce the C3S content, and that is exactly what is seen here. We see that with C2S, the extent of heat release is minimal as opposed to C3S or C3A. Now, the person who formulated the Bogue equations, Bogue himself, also stated about the heat that half of the total heat is evolved between 1 and 3 days, and about 3/4 of the heat is evolved in 7 days, and about 90% of the heat at 6 months. So what does he mean? Actually, if you continue to cure a cementitious system, it will continue to react, and when it reacts, it will continue to liberate heat even for a very long period of time. Okay. So when we are looking at very short periods of time, let's say 1 to 3 days, we are already releasing about 50% of the heat. Now approximately this also matches very well with the rate of strength gain of your cement. Okay. If the total heat that is released is 50%, your cement is also gaining about 50% of its ultimate strength. Okay, that's why even if you look at the 7 days data, three-fourths of the heat is expected to be released by 7 days, which means that approximately 75% of the potential strength will be obtained with this cement in the concrete at 7 days. Now what does this mean as far as curing is concerned? That means that curing at 7 days would be sufficient enough to provide us a strength gain of at least 75% of the ultimate strength, and that is the reason why in most practical considerations we have 7 days as the limit for curing. Okay, because this heat development matches quite well with the strength development, and by 7 days you have sufficiently good strength development in the concrete to stop the curing, and because after that it does not really pay much dividend to continue to cure much further. Okay. So anyway, so that's the rate of heat evolution, but please remember I have presented in this table the total heat that is getting evolved from 1 gram of each of these materials reacting. Now the total heat is one thing, but the other aspect that you need to understand is the rate at which heat is evolved. Now what is the difference here? Now supposing all my heat is getting evolved within 1 day, as opposed to that I am evolving heat over 7 days. So that means my rates of heat evolution are quite different, although the total heat liberated may be quite similar. Now the significance of this is when the rate of heat evolution is very high, you have chances of thermal cracking occurring in your structure. Why is that? Because your concrete raises its temperature when the cement hydrates and increases in temperature or liberates heat. So the concrete raises its temperature, and when it starts to come back to the normal atmospheric conditions, there is going to be a reduction in temperature. So there will be a contraction, and any expansion or contraction in concrete will obviously have a very large effect on the cracking potential of the concrete. So when you have a very high rate of heat evolution, there is a very good chance that your concrete will end up cracking. Okay. So please remember the total heat evolved is dependent or is related to the actual evolution of the compressive strength, but the rate of heat evolved is very important from the perspective of understanding thermal cracking of cementitious systems. So very high rates of heat evolution are not good for the cement, especially in cases, for example, you must have heard that very high strength cement should not be used, for example, in plastering applications. Why? Because there you have a very large surface area, a great chance of shrinkage and thermal stresses to be very high, and when you have fast reacting cement, these stresses are liable to produce a lot of cracking. So when you do plastering, you need to use a cement that is fairly low in strength so that it does not crack. Okay. Alright, so coming back to our discussion on heat evolution, if you look at the rate of heat evolution, you need to measure it with the help of a suitable calorimeter system. Okay. Now without getting into the details of calorimetry, I just wanted to tell you that calorimeter is simply measuring the heat that is getting evolved in this reaction. So there are different ways of doing it. There is one thing called adiabatic calorimetry and another called isothermal calorimetry. Now adiabatic calorimetry obviously implies that the system in which the cement is hydrating is kept in a condition which prevents any loss of heat to the surrounding or any input of heat from the surrounding. Okay, so that's an adiabatic condition. In an isothermal calorimeter, what is done is you attempt to keep the temperature of the sample constant. Now how will you keep it constant if it's liberating heat? You will keep it constant by extracting the heat. So you extract this heat and then you look at how much heat is getting extracted with respect to time as the cement hydrates. So I'll come to the actual charts that show you the heat evolution, but I'll just show you a calorimeter that we have developed within our IIT Madras laboratory, which is called an adiabatic calorimeter. There are several details with respect to this calorimeter which are available in an Indian Concrete Journal paper in the May 2013 issue. Okay, so if you want more details on this, you can definitely write to me, or probably refer to this paper which gives you an idea about how to make this calorimeter on your own. It is not very difficult, and the advantage with the adiabatic calorimeter is you are not necessarily only testing the cement, you can actually test the actual concrete mix that you are designing for the project and see how much heat is getting involved from this. Okay. So without too much further detail, I will go on to the actual heat evolution pattern that is produced during cement hydration. That is definitely of more practical significance to what we are talking about here. So I will just walk you through this diagram first. So on the y-axis you have both total heat and heat rate that are plotted. The solid line or the solid curve that you see in the graph is the total heat, and the dashed line which you see like this is actually the rate of heat evolution. Now please remember, we will talk mainly about the rate of heat evolution because that is what is actually getting captured by our cementitious reactions. Okay. And on the x axis you have the time plotted in hours, okay, approximately the time in hours. So if you look at the rate of heat evolution, as soon as cement and water come into contact, there is a very high heat liberation, which is also known as the initial heat burst. Okay, so what is happening here? As soon as you are wetting the cement particles, there is an immediate reaction that is happening, and also we call that as heat of wetting. So that is actually generating very large heat or very large rate of heat. Please remember, we are not generating too much heat that the cement actually ends up setting. It is not happening in the normal cement case. Okay, here this initial heat burst is only because of the initial surface reactions that are actually happening with the cement particles. It is not really anything to do with the actual setting process. Okay, so the rate of heat evolution is very high, but if you look at the total heat graph here, the total heat produced during that very small interval of time is very minimal. So you are not even plotting that on this graph, you are not even seeing a heat development of this graph. Okay, so you form a very high rate of heat evolution right in the beginning, but that is not of any consequence at all. As soon as that is obtained, the heat rate actually comes down. You see here that you have a period of very low heat rate. Mind you, it is not zero. That means the reaction is not discontinuing there, it is still continuing, but then you have a very low heat rate, and then you see a sudden rise in the heat rate. After a certain period, let us say 2 to 4 hours, you see a sudden rise in the heat rate, and you culminate in this peak which is named as the main peak of hydration. You see, this is the main peak of the hydration process. Okay, and then beyond that main peak there is a slowdown in the rate of heat evolution. Okay, and then it comes down, and you may or may not pick up this secondary peak. You see here secondary peak, which I have marked here as AFT to AFM. I will explain that in just a minute. Okay, so AFT to AFM is marked here. After that the rate of heat evolution seems to decrease, and then it continues to go close to the axis. That means I am not ending up with a zero rate of heat evolution. Please remember that as long as I am providing water to the system, there is going to be continued hydration. So as there is continued hydration, there is going to be continual heat development in the system, but the rate of heat evolution is dropping considerably after this point where I have obtained the main peak. If you look at the total heat evolution, you are slowly building this up, and when you are going towards the main peak, the total heat development is very high, and after that it sort of slows down. The total heat that is developed sort of slows down and tapers off to a very slow rate. Okay, please remember, as long as I am curing the system, the cement is continuing to hydrate, and the total heat will keep on increasing. Okay, although by a very small margin. Okay, so now let us try and understand the meaning of these peaks and what reactions they can be attributed to. So the first peak, as I said, the initial heat burst, as I said, is only because of very early surface reactions that happen on the surface of the cement particles, and we also call that as heat of wetting. Okay, after this we see a period where the rate of heat evolution is very small, and that period, which is marked in the previous graph as D here. Okay, this D basically is dormant period. Now what does it mean? Dormant period means the reaction rate is so slow that I am not evolving much heat at all. Okay, that does not mean that the reaction has stopped. It has not stopped, it is continuing to happen, but at a very slow pace. Okay, that is why we call it as dormant period, where we have a very slow rate of heat evolution. Now this peak 2 or main peak, which I showed you in this graph, this main peak here, okay, that is basically the peak which is associated with rapid dissolution of C3S to form calcium silicate hydrate, and calcium hydroxide. Please remember, in cement chemistry, C is calcium oxide, S is silicon dioxide, and H is water. Okay. So when I say CSH, it is some mixture of calcium oxide, silicon dioxide, and water. When I say CH, it is actually calcium hydroxide. Okay. So at this main peak, my C3S is rapidly reacting with water to form CSH and calcium hydroxide, and I also form ettringite, which is actually a product of the reaction between C3A, that is your tricalcium aluminate, and the gypsum that is added in the cement manufacturing process. Please remember, we added this gypsum in the cement manufacturing to control the rate of C3A hydration. Okay, so in the presence of this gypsum, it produces this ettringite, which is actually a calcium sulfoaluminate phase. Okay, I'll come back to the actual reactions later, so you can actually see. Then you see a slowdown of the hydration. Okay, so you have a very low rate of heat evolution. Beyond that, you may or may not pick up a third peak, which is associated with the conversion of one form of calcium sulfoaluminate to another form. Okay, so from ettringite, we go to a phase called monosulfate. Okay, so I'll talk about what these sulfate phases are and what are their significance in the actual cement chemistry. Okay, I'll skip this because this is not very central to the discussion we are having in the system. What I really want you to understand is cement contains very highly soluble alkali oxides. Look at this last point here, that cement contains very highly soluble alkali oxides. Please remember, we have sodium oxide and potassium oxide, and because these alkalis are highly soluble, my pH of the concrete system is extremely high. Okay, the alkalinity of my system is typically more than 13. Okay, and even when I replace cement with mineral admixtures like fly ash or slag, my pH still remains to be as high as around 12 or 12.5. Okay, now why is this pH important? This pH is important because this is what maintains the reinforcement steel that you put inside your concrete in a stable condition. If your pH reduces to less than 11, then your steel can start corroding. So generally in a cementitious system, or even a cementitious system which has fly ash or slag as replacement of cement, your pH is always greater than 12 or 12.5, which enables your steel to be in a passive condition without corrosion. Okay, so that's only point I wanted to actually bring out from here. I'm not going to dwell on this much further. I want to move on to the next point to show you how the water to cement ratio actually affects the rate of heat evolved in the system. Okay, now in this case, I'm just showing you a very basic diagram here on the top left here, which is basically the rise in temperature inside the adiabatic calorimeter that we had developed with respect to the time that is elapsed, and this has been plotted for 5 different water to cement ratios. Now without really having to struggle to look at that data, I'll just walk you through this data in this table here, which tells you what happens when I change the water cement ratio of my system to 0.4 to 0.45, 0.5, 0.55 and 0.6. Okay, if you look at this peak heat rate that is getting evolved, please remember the peak heat rate corresponds to the main peak that I saw in my heat rate pattern. Okay, so peak heat rate, as I increase my water cement ratio, the peak heat rate is dropping from 7.7 to 4.19. Between a heat rate between a water cement ratio of 0.4 and 0.6, my peak heat rate has dropped to almost half of the heat rate at the low water cement ratio. So what does this mean? To produce very high rates of heat evolution, you need to have lower water to cement ratios. Now again, how do you produce higher strength concrete in your mixed design process, and how do you produce higher early strength concrete? By reducing your water to cement ratio. So exactly that's what we are capturing here. When you reduce your water to cement ratio, you have greater rates of heat evolution. Now while this means that you also have a greater strength development, please remember that this also means that you have increased the risk of cracking with your concrete. Okay, when you have a greater rate of heat development, you have a greater risk of cracking. So when you reduce water to cement ratio, the risk of cracking increases. So you need to ensure that you are protected against that by providing a proper mixture design for your concrete system. Okay, so the peak heat rate has reduced. The time to peak heat rate, that means how long has it taken before the peak heat rate has been achieved. Now that has been increased as I increase the water content in the system. Okay, that's also something which we can easily understand because the rate of reaction is going to get slowed down. You have much more water in this case. Okay, so the water will take a much longer time to actually heat up in the system. So as a result of that, you're getting a much slower rate of heat development as far as the higher water cement ratios are concerned. Even if you look at the peak temperatures that have been reached in the system, you see 70 degrees in the case of 0.4 water cement ratio and 59 degrees in the case of 0.6 water cement ratio. If you look at the strength development at the early ages, 3 and 7 days, you clearly see the effect of lowered water cement ratio. You see much higher strengths at very early ages itself with the low water cement ratio system. And of course, at the highest age at 28 days, you still expect there to be a major difference in the strengths because your water to cement ratios are quite different. Okay. So I wanted to show you how we can actually capture the effect of water cement ratio on the heat development directly with the help of this calorimeter. Now when you have a pozzolanic material like type F fly ash or type C fly ash, how does that affect the rate of heat evolution? Again, I have shown the diagram on the top right image here, but again I will show you the table which will make you understand these much better. So here in the table I have the control mix, which is my plain Portland cement concrete mix. I have the type C fly ash replaced mix at 20%. I have type C fly ash replaced mix at 30%. Please, just for your information, type C fly ash means that it is a fly ash which is high in calcium oxide, like the fly ash that we get from Neyveli. Okay, but type F fly ash, which is presented in the last two mixes, is something that has low content of calcium oxide and a high content of silicon dioxide. So it's a siliceous fly ash. Now you see directly the effects of these. When I use a type C fly ash, my heat evolution is not that much affected as opposed to a regular cement. That means I have not reduced my heat evolution by that much. But if I use a type F fly ash, my heat evolution reduces drastically. Okay, so one option for you, if you didn't want to use a low heat cement because it's not available, is to simply use type F fly ash as a replacement for cement. By even 20 and 30%, it is almost reducing your heat evolution by half. So that's a very big contribution from the fly ash. Reduced rate of heat development. That's a really huge contribution. Now if you look at the rate of strength development also, these are going to be lower when the rate of heat development is lower. Okay, so that means that you need to cure your system for a longer period of time to get the same degree of strength development. Alternatively, you need to redesign your mix to obtain the same degree of strength development. Okay, so strength development is again, as I said, related to the total heat development, but the rate of heat evolution is related to how fast your cement is reacting within the first 24 hours. So when you have fly ash as a replacement for cement, you really produce a much lower heat of hydration. So that's a major benefit of using fly ash as a replacement for cement. So again, why does this dormant period occur and what is its significance? Please remember one thing, when you're mixing cement and sand and stone and water together to make your concrete, you need certain minimum amount of time during which you are actually working with the concrete, because you need to mix the concrete, you need to convey it to the job site, you're delivering this into the formwork, you're then compacting it, then finishing it. So many different operations have to happen without the cement actually setting. Okay, so this dormant period is very crucial because the duration of this dormant period usually tells you the duration of the setting period, how long actually it takes for the cement to set. So this dormant period is very crucial from the point of view of application of the cement in concrete. And it happens because when you're mixing cement with water, you form this initial hydrate layer which sort of slows down the reaction. Okay, and that is very crucial for us because we get the time required to actually work with the concrete. There are several theories that you can actually read the slides on your own. It's not really something that we need to be concerned with, but the fact that it really contributes to the overall performance of the concrete is what is important for us. Okay, so moving on, after the dormant period, as I said, you have the main hydration reactions that take place. Now let's take a look at these hydration reactions in some detail. I have actually presented a brief summary of the reactions here. I'll just go through these so that you can understand what I'm talking about. So the silicates, that is C3S and C2S, react with water to produce calcium silicate hydrate, which is written as CSH, and we call it as gel because we don't know its structure very well. I'll talk about its structure a little bit later. And then you have calcium hydroxide, which is actually a very well crystallized material. Okay, now you produce much greater quantities of calcium hydroxide with C3S as you do with C2S. Okay, more calcium hydroxide is produced with C3S. I'll give you the approximate reactions so that you can actually appreciate this better a little bit later. Now CSH, as I told you, does not have a very clear cut structure, nor does it have a very clear cut composition. Okay, the CSH has a varying composition. The calcium to silica ratio in CSH varies generally between 1.5 and 2. Okay, calcium to silica ratio, C by S ratio, that is what is written here, varies from about 1.5 to 2. Okay. Now the aluminates, that is C3A and C4AF, if there is no gypsum present, please remember, if there is no gypsum, my aluminates will react rapidly with water to form calcium aluminate hydrates, CaH. But we are not interested in that, we are only interested in what happens in ordinary Portland cement, and that is in the presence of gypsum, you form ettringite and monosulfate. Okay. Now how do you produce this and where does it produce? Again, we will see in the reactions that are presented in the next slides. So the specific reactions, please remember, these are not perfectly balanced reactions or perfectly accurate reactions. There are several different versions of reactions that you can find from different textbooks. Okay, I urge you to look in the content in the textbooks to look at the different reactions. I have presented this just because this is a simple reaction to look at. Okay, so you have 2C3S plus 6H is water, please remember H is water, 6 molecules of water giving you 1 CSH, that is C3S2H3 and 3 calcium hydroxides. Okay, so C3S2H3 means 3 CaO, 2 SiO2 and 3 H2O. Okay, I'll write that on the board just for clarity. C3S2H3 is simply 3 CaO, 2 SiO2 and 3 H2O. That's the molecule that is formed of CSH, calcium silicate hydrate. Okay. Now when you react C2S with water, the reaction is slightly different. So here you have 2 C2S plus 4H, that means 4 molecules of water gives one part of the same CSH or C3S2H3 and only one part of calcium hydroxide. This is what I was saying, that when you react C3S, it produces 3 times as much calcium hydroxide as you do with C2S. So again, one thing you might have seen earlier when we talked about different types of cements is that when you have cements that are high in C2S content, they gain strength slowly in the beginning, but then the ultimate strength is much higher than the ordinary Portland cement, which has much higher C3S content. Now why is this the case? This is the case because for every gram of C2S that is reacting, you are actually producing a greater proportion of CSH as compared to C3S. So long term strength definitely depends on C2S hydration. But in modern Portland cement, where C2S is not really hydrating or contributing in the early stages, we are not really interested in that. Okay, we only want up to 7 days or up to 28 days strength, and most of the strength in this period is actually contributed by your C3S content. Okay, now let's look at the reaction of C3A. Now without gypsum, C3A reacts with water to form this calcium aluminate hydrates, which are again metastable phases that convert into other phases. Let's not talk about that right now. In the presence of gypsum, okay, C3A reacts with gypsum. Gypsum has been written as CS bar H2, S with an underline at the bottom. So S bar is actually not silica, it's sulfate, SO3. Okay, please remember I had discussed this in the cement composition chapter earlier. Okay, so C3A plus gypsum with a lot of water, 26 molecules of water, gives you ettringite, which is basically 6 CaO, Al2O3, 3 SO3 and 32 H2O. So just for clarity, once again on the board, C6A S bar 3 H32, that is nothing but 6 CaO, Al2O3, 3 SO3 dot 32 H2O. So that's what is ettringite as per the cement chemist notation. Okay, so please see that it actually holds a lot of water in it, and the formation of ettringite is also known to be expansive. Okay, so in the initial stages when ettringite is forming, your cement paste is actually expanding because of formation of ettringite, but that's not crucial because your cement paste is still plastic, it is pliable, okay, it's not hard yet. Only when it's hard and if it's forming ettringite, then you're going to be starting to crack the system. But here your cement paste is still fresh, so even if ettringite forms and expands, it's not really a big concern, okay. So ettringite actually forms in the system like this. But what happens to this ettringite? Does it remain stable in a regular Portland cement? The answer is no. Now why does it not remain stable? It's because in a normal Portland cement, you have much higher content of aluminate as opposed to sulfate, okay. So what will happen to this ettringite is this ettringite will again go into reaction with the excess C3A that is left in the system and form what is this phase called monosulfate, C4AS bar H12. You see this phase here, C4AS bar H12, that's the monosulfate phase. Now why is this reaction important? This reaction is important because in a final assembly of the phases that you have in your cement, you will find that ettringite is not really present after about 7 days or 28 days. All of it would have got converted to monosulfate phase because you have excess of aluminate present in the system, okay. Now this is important from the point of view of sulfate resistant cement, okay. Please remember last time when we talked about sulfate resistant cement, the common point there between the standards was that in sulfate resistant cement you have lower C3A content, okay. In normal Portland cement you have higher C3A content. Now why is that crucial? Because in normal Portland cement, because of the high C3A content, your end product is monosulfate, whereas in sulfate resistant cement, because of lower C3A content, your end product of hydration is ettringite. Now why is this sulfate resistant cement actually resistant to sulfates? Because when you have external sulfates coming into this system, the ettringite is already stable in that system, so it does not react. But when the sulfates come into a normal Portland cement system, the sulfate will react with monosulfate and convert it back to ettringite. Now this conversion is happening when the concrete is already hard. That means this ettringite is going to expand inside hardened concrete, that's going to result in cracking, okay. So that's why normal Portland cement cracks in the case of external sulfate attack, and sulfate resistant cement is stable in the case of external sulfate attack, because ettringite is stable in sulfate resistant cement after initial hydration. In normal Portland cement, monosulfate is stable after the initial hydration period, okay. Now there is not much difference between the reaction of C4AF and C3A, except that your ettringite and monosulfate that are forming, apart from the alumina, they will also contain some iron in the system, okay. I am not going to get into that reaction in detail here, but I just want to tell you that reaction is quite similar, that it produces ettringite and monosulfate which are iron substituted, which do not have only alumina but also have iron in them, okay. How these hydration products are actually filling up the space, okay. If you look at the bottom left here, the small graph that I am showing you here just shows you a picture of what happens when you put cement inside water. The black particles are those of cement, okay, and those are being put inside water. So as I told you, as soon as cement is put inside water, there is some early hydration that happens and you have a barrier layer or layer just forming on the surface of the cement particles here, okay. You see that layer on the surface of the cement particles, and that's approximately the time that you have your dormant period. So again, look at this process here, this is happening in the first 2 hours of hydration of cement, and after that period, after about 2 to 4 hours, you start forming a network of your hydrated products. Your CSH starts developing, okay. You see here, this is again marked by an increase in the quantity of your CSH, okay. The top graph shows you, okay, first in the initial stages you are only forming some ettringite and calcium hydroxide, but later you start forming CSH, and when you start forming CSH and create a network of hydrated products, that's when you have your setting, okay. So for years you have been doing the YCAT test for setting, right, and the YCAT test for setting is some arbitrary test which looks at the needle penetration and all that. Now why is it called setting? Because at that point you have formed a hydrated structure that is interconnected, which resists the penetration of the needle. That's exactly what is the true meaning of setting, that you have a hydrated structure which is forming here, and that's where you get your setting. That's because of the CSH that is and ettringite that have sort of developed and formed a network, okay. So as the setting progresses, as hydration progresses, more and more of the space gets filled up, and you ultimately get a space that has very little void content. You have occupied almost the entire water filled space by the hydration product, because of which your strength continues to go up, okay. and that strength going up is also corresponding to the CSH, which continues to go up. So that's your CSH, which continues to go up, and as CSH is going up, obviously your calcium hydroxide also has to go up, because that's also another product of the hydration of your silicates with water. Okay, so that calcium hydroxide goes up, calcium silicate hydrate goes up. Ettringite, which is this dark line here, peaks at during the setting time, but after the setting time the ettringite is dropping. Why is it dropping? Because it's getting converted to monosulfate. You see, as ettringite drops, this phase called monosulfate picks up. Okay, monosulfate picks up, and you have also so much excess aluminate available in the system that you actually also form aluminate hydrates or aluminoferrite hydrates, which is what is marked here. So if you look at 90 days, if you look at the end of this chart at 90 days, the stable phases in your system, the highest quantity is that of calcium silicate hydrate, CSH, then you have calcium hydroxide, then you have your monosulfate and calcium aluminoferrite hydrates, and you may or may not have any ettringite left in your system. Okay, that's the final phase assemblage that is actually possible in your system. The right side graph is also showing you the same picture from a different textbook. Okay, all this is showing you is how these other phases are developing and ettringite is actually reducing with time. Okay, so the same sort of chart is being presented on this side also. How does this relate to the actual development of strength and reduction of permeability? Once again, please remember, around the time of setting is when I'll start my strength development process. So my initial set is here, the final set is here, and beyond the final set is where my strength actually starts developing. Okay, but your porosity in the system continues to come down even from the early stages. Okay, your porosity and permeability are actually coming down significantly even when your concrete is actually just setting. Okay, why is the porosity coming down? Because the water is getting used up by the cement to produce the hydration products, and these hydration products are actually going and filling up the space, reducing the amount of porosity that is actually available. Okay, so with time, as hydration continues, the strength continues to develop, the porosity continues to reduce, and the permeability continues to reduce. Okay, so that means if I continue to cure my system, if I continue to ensure that water is available for reaction with cement, my strength will go up and my permeability will come down. In other words, as the permeability comes down, my durability goes up. So strength and durability will go up as I continue to cure my system. So please remember, curing is from the viewpoint of ensuring that you have an environment of 100% relative humidity that permits the water to continuously interact with the system and hydrate the cement, which leads to this reduction in porosity and permeability. Now again, this is a schematic diagram which again shows you the development of the hydration products. I am not going to go into details of this because it's self-explanatory. Actually, you can read this when you get the slides. Now these are some pictures taken by microscopy of how the cement is actually hydrating. I told you earlier that the particles of the cement, that is C3S and C2S, dissolve outwards. Okay, this is actually showing you one such particle. This is actually one such particle which is dissolving outwards and forming these hydrates on the outside. These are the hydrated particles that are forming outside. This is a particle that is dissolving, and this is a space which was previously occupied by a particle which has got completely dissolved, and you only have the hydrated phase around it. Okay, this particle has got completely dissolved here. It's completely hydrated to form the hydrated phase that is going around it. These are also known as Hadley grains. Okay, but again, that's not of much significance to our discussion right now. This is a typical microstructural picture of what you see inside a concrete after the hydration of the cement. Okay, I'll just walk you through this picture once again. You have these large particles, those are of sand. Okay, you have here large particles of sand, these are sand particles, and between the sand particles is your cement paste. Within the cement paste, you have this cement grain which is looking very bright. Okay, that's a very bright looking cement grain, and there are several other darker phases. The completely black phases, you see completely black spots, several of them, those are basically your pores and voids which are there in the system. Okay, I'll come back to pores a little bit later, pores and voids. Okay, those are the pores and voids. The light gray phases which are surrounding the cement particles are your CSH, calcium silicate hydrate phases. Okay, and then the bright white, which is not as white as the unhydrated cement grain, but still the bright white phase is actually your calcium hydroxide. I'll show you more pictures for clarity. Sometimes your calcium silicate hydrate forms in two different types, okay. Sometimes it forms right outside your grain, or sometimes it forms away from the cementitious grains. When it forms right outside the grain, as is shown in the left side image, it is called as inner CSH, and when it is formed slightly away from the grain, as what is shown here in the dark gray faces that are surrounding these grains, it's called the outer CSH, okay. Now that's just related to the way that the hydration happens. Very early in the process, the outer CSH starts forming because your smaller grains of calcium silicate start dissolving and hydrating outwards. Now after you form this initial hydrated layer, water gets through this hydrated layer by diffusion, reaches the unhydrated grains of cement and starts reacting at the grain itself, and that's the reason why you start forming these inner CSH layers. And this happens typically at a much lower stage as a much later stage as opposed to the outer CSH formation. So the early strength that you see at 1 or 3 days is just because your outer CSH is forming very fast, okay. The later strengths are because your overall structure including the inner CSH is developing and reducing your porosity slowly, okay. So there are several distinctions which I am not going to talk about here because it is not probably within the scope of our discussions. I will move on to the next picture, which again shows you a distinction between the inner and outer products as viewed by microscopy. So again I am not going to talk in detail about this. The idea is just to show you the differences in the hydration products that are actually forming. You have this hydration product forming right outside your cement grain, that's your inner CSH, and then you have the outer product which is looking a lot more darker and less dense, that is your outer CSH. And open the floor for some questions, because you can clarify your initial doubts on cement hydration, because the later stage we are going to talk about how the structure actually develops, what are the structure of different hydrated phases, and how is the cement chemistry which we are looking at in terms of the reactions of hydration, how is this going to control the properties of concrete in the long term, okay. Let you ask some questions. Yeah, you can also interact directly with the chat if you have a question that is there in the audience. Okay. Alright, so now there's a question about what is the difference between flash set and false set, okay. Please remember I talked about flash set earlier. That happens when you have a cement that does not have gypsum, okay. The aluminates in the absence of gypsum react rapidly with water to form the aluminate hydrates, and that is flash setting. At that point your concrete becomes unusable, okay. Now false set is something different. False set is, sometimes you might have seen that when you add your water to the concrete mixture inside the mixer, it starts stiffening, the concrete mix starts stiffening, and that is happening for about 1 or 2 minutes, and after you continue to mix, that stiffening goes away. Now that happens because this gypsum that is actually available in your cement may be in different forms. Sometimes the gypsum may be available as a plaster of Paris form or an anhydrite form. So when you have water which comes into contact with the plaster of Paris or anhydrite, this product gets converted again to gypsum, and this temporary conversion to gypsum of these other forms of calcium sulfate is responsible for false setting. As the name implies, it's only a false set. That means it's something that you can break through, okay. It is not the ultimate setting of your concrete, it's a false set that happens because of conversion of other calcium sulfates to gypsum. Whereas flash setting happens when there is no gypsum present, the aluminates react rapidly with water. Okay, one question on what is the dormant period. Again, the dormant period is the early phase of cement hydration when you are evolving very low rate of heat, okay. As I told you earlier, it's got a very practical significance because you need some time to work with the concrete to ensure that you are able to mix it, place it, compact it and finish it, okay. All this has to happen. So dormant period is responsible for ensuring that we are able to work with this concrete during that period of the first 2 to 3 hours when our setting has not been achieved, right. So that's the significance of the dormant period. So dormant period is just a stage where rate of heat evolution is less. I'm not saying that it's zero, it is just low. The rate of heat evolution is just low. Okay, relationship between heat of hydration and strength of cement. Please remember earlier I told you that the total heat evolved is very well correlated with the rate of strength development of the concrete. So if you are able to measure the heat evolved in the process, you can easily correlate that with the strength of the concrete. So generally the higher the rate of, sorry, not the rate, the higher the total heat evolved in the system, the higher will be your strength, okay. The rate of heat evolution is only telling you how fast you are achieving this heat, okay. So that's more crucial from the point of view of the early stages, but overall if you look at 3 days, 7 days, 28 days and all that, you can very well correlate the strength development with the total heat that is getting involved in the system. How can cracks occurring be repaired without demolishing? Okay, now that's of course it's a difficult question to answer. Depends on at what stage you are seeing the cracks and at what size the cracks are, okay. So you might know that several times cracks appear very early after the concrete has been placed, and that's called plastic shrinkage cracking. Now these plastic shrinkage cracks, if you catch them at the moment that they appear, as soon as they appear, then you can simply take a wooden float and rub on top of the shrinkage cracks and they'll go away, okay. So that's the practice that is commonly followed by people who are looking at cracking in slabs at very early stages. We are talking still about the first 5 to 6 hours after placing the concrete, and that's the crucial stage for your plastic shrinkage cracking to appear. But if the cracks are appearing in hardened concrete at a very late age, then there are several techniques by which you can actually repair the cracks, assuming that they have not really contributed to the lowering of your structural capacity. If they are only superficial cracks, you can repair them by opening up the cracks a little bit and then grouting them with a low viscosity grout, which goes and fills up the cracks and totally blocks the space. But if this crack has led to something bigger like your corrosion of the reinforcing steel, then you need to seek a much different solution. You probably need to open your concrete until the portion that you see the reinforcing steel that has been corroded, make a treatment for the corroding steel and then fill up the remaining area with concrete. So several different mechanisms are available for repair of cracked concrete, but depends on when you catch the cracking and how big the cracks are. Okay, so what is the influence of climate on the heat of hydration? Actually it's a good question, because when you are making concrete and placing it in a very hot climate, the speed at which the reactions are happening also are large. Your system is also getting heated up, so the actual heat that is getting evolved also increases as you have external heat being supplied to the concrete system, okay. So definitely your rates of heat evolution are going to be much higher on warmer days, which is why it is very important when your weather outside is very warm that you should use a retarding admixture that retards or slows down the rate of reaction. Alternatively, instead of regular water, you can use either cold water or ice to reduce the temperature of the concrete, okay. That's what is typically done in most sites where you're, especially when you're doing very large volume concrete pouring, like for raft or for mass concrete like dams and so on. Okay, what is the function of C4AF in cement and what is the role of C4AF in concrete hardening process? Please remember I told you earlier that C4AF does not differ too much from C3A in terms of its reaction. Only the fact is that C4AF reacts much slower than C3A, okay, it reacts much slower than C3A, it takes a longer time to react, but then it ultimately produces similar products as C3A. The only difference being when you produce ettringite with C4AF, it is not expansive. With C3A, the ettringite is expansive. That's why in sulfate resistant cement, we have lower C3A content and higher C4AF content as compared to ordinary Portland cement. So please remember that's a distinction between C3A and C4AF. Okay. Okay, there's an interaction with Amrita. Do you have a question?
My question is there any difference in the structure of outer and inner CSH?
Okay, yeah, I have not got to through those details because of the time involved, but anyway, I'll tell you that in general, the structure itself is not that different. It's only the way that the CSH is formed and the packing that is quite different. The porosity, the outer CSH is generally much greater. The inner CSH is much more dense as compared to the outer CSH, okay. But primarily the porosity in the outer CSH is what ultimately controls the porosity and permeability of your cement paste itself, okay. So the outer CSH porosity is much more as opposed to the inner CSH, okay. And the structure difference is primarily on the account of how much of other products are available within the CSH. When you look at outer CSH, it is usually rich in monosulfate. A lot of monosulfate is present inside the outer CSH in very small crystalline shapes, okay, which cannot be detected very clearly as deposits. So outer CSH is highly porous as opposed to inner CSH. Outer CSH also has more monosulfate present in it, whereas inner CSH is more or less pure. Okay, so that's the main difference between outer and inner CSH. Okay, how the heat of hydration varies from OPC to low heat cement. Of course, I don't have data to show you here, but very clearly there's a reduction in the total heat that is released when you have low heat cement. More importantly, the rate of heat evolution is going to be reduced considerably when you have low heat cement instead of ordinary Portland cement. Is CaO present in type C fly ash good or bad to cement? Now again, please don't call it good or bad. The presence of the calcium oxide in type C cement makes it more reactive as opposed to a type F cement. Okay, so if you are looking at high reactivity from your supplementary cementing material, then it's good. But if you are looking at reduction of heat of hydration, that's not going to happen very effectively when you use type C fly ash. So it's not good or bad, it's just producing a different kind of reaction, that's all. Okay, so that's the only difference. How does fly ash reduce the heat of hydration? Now of course the question is related to the lower heat of hydration observed with type F fly ash. Please remember, type F fly ash is siliceous fly ash, and if you have seen the images for how this fly ash looks, they are actually spherical particles of fly ash, and these siliceous particles have to react only with the hydrated lime, that is calcium hydroxide, that is generated during cement hydration to produce CSH. So this reaction is very slow, the pozzolanic reaction, which is basically a reaction between the reactive silica and calcium hydroxide to produce CSH. That is actually a much slower reaction as opposed to regular cement hydration. That is the reason why when you replace cement with fly ash, you lower the rate of reaction and automatically lower the rate of heat evolution. And sometimes most fly ashes also have a glassy bubble in which the actual reactive particles are located. You need to actually break through this bubble and release those individual reactive particles of silica to really produce the pozzolanic effect, okay, which is why in normal fly ashes you see a lot of set retardation and lowering of heat of hydration. Okay, there are special fly ashes available where people have processed the fly ash to obtain the smallest reactive particles out, and that is also called classification of fly ash. And in that classification process, since the reactive particles come out, the reactivity of fly ash is increased tremendously. Okay, so these are actually available as products nowadays for replacement of cement in concrete. Which compound in cement is responsible for converting fly ash cementitious? I am not able to understand that question. Fly ash is cementitious because of its own calcium oxide content, which is type C fly ash has high calcium oxide content, that's why it's cementitious. Type F fly ash is not cementitious, it's only got high component of silica, not of calcium oxide. Okay. Again, this other question, if so, what is the proportion of the compound required for making certain quantity of fly ash cementitious? That's really not valid, because again, fly ash is cementitious because of its calcium oxide content, not because of the cement. Okay, when it is cementitious, it's going to react faster. When it is siliceous, it is reacting only with the calcium hydroxide produced during cement hydration process. Okay, how do you determine the thermal expansion coefficient of cement is the question. Now again, thermal expansion coefficient has to be determined by controlled experiments in which you actually increase the temperature of your cement paste or concrete and measure the linear expansion that actually happens inside. You can measure the linear expansion either by the help of a Demek gauge, or you can use a strain gauge to measure the linear expansion that happens when you change the temperature between low and high temperature. Okay. Explain the significance of crystalline form in cement chemistry. Okay, now please remember, when we talked about cement composition, we also saw how these different compounds are different in their appearance and in their crystalline forms. So different crystalline forms contribute to different levels of reactivity. Okay, please remember we talked about C3S, which is present in different sorts of forms, monoclinic, triclinic and so on, and the grain of C3S itself had a very irregular shape, and that irregularity in the shape of C3S leads it to have a high rate of reactivity. On the other hand, C2S is much more rounded and has a much lower rate of reactivity as opposed to C3S. I am not going to go into the polymorphic forms because polymorphism again is a subject that requires a lot of debate and understanding. We have not really covered that level of detail in our discussions in the last two chapters. So let us not talk about that at this stage. In general, the reactivity is associated with the fact that you have your cement particles present in an irregular form, and secondly that you have several impurities like impurity oxides that I showed you in the last class that are also present that contribute to this high reactivity of C3S. There is a question on what is ettringite. Okay, ettringite, I had shown you the expression for ettringite. Ettringite is the product of hydration of C3A in the presence of gypsum. So C3A combines with gypsum and water to produce this compound called ettringite, which is basically calcium oxide, aluminum oxide, sulfur trioxide and water combined in a definite stoichiometric proportion. Okay, I had shown you earlier on the board, it's still there on the board, you can actually see it. The ettringite actually has C6A S bar 3 H32, okay, which is 6 CaO Al2O3, 3 SO3 and 32 H2O. Okay, that's your ettringite. And ettringite formation in fresh concrete is not really a problem, but when ettringite forms in hardened concrete, it is associated with an expansion which creates cracking in hardened concrete. That is what happens in the case of external sulfate attack. Now some people have asked some questions in the chat window also. Here there is a question is, what are different techniques used to reduce heat of hydration in large construction like dams? I have already talked about that. Essentially you replace cement by fly ash, that is one option. Second is you can replace water by cool water or ice construction. And third, which is largely followed in dams also, is to provide some internal network of cooling, like putting cooling pipes through the concrete, which actually reduces the temperature of your concrete and keeps the heat of hydration down to a significantly low extent. Okay, again ettringite I have answered. How aluminate sulfate play the important role in OPC? Okay, so two important things. One is formation of ettringite happens during this main peak of cement hydration that is responsible for the setting of the cement itself. Okay, so ettringite formation produces these needle like structures. I will show you pictures later. Needle like structures which are occupying a lot of volume in the cement create an interconnected network of hydration products, and that leads to the setting of your cement. Okay, so that is your ettringite formation in early stages. It is important also because ettringite formation produces expansion when you have sulfates attacking the concrete from an external source. So your monosulfate that is present in the cement converts to ettringite in a hardened concrete, and that causes sulfate attack related expansions which lead to failure of your concrete. How much time does C3S react with water and how much energy is produced? That is another question. Now I do not really have a clear cut understanding of this, because as I told you earlier, as long as you provide water in the system, as long as you continue to cure your concrete, the cement will continue to react. So even if you take a 1-year-old concrete, you might even still find C3S particles that have not hydrated completely, that are still in the process of hydration. Okay, so there is no specific time for this, but you can imagine that the smaller particles of C3A will react very fast, the larger particles of C3S will take a longer time to react. Okay, so there is no clear understanding of how long it will take to completely react the C3S. Okay, because it may not be physically possible for that to happen also, because after concrete becomes very hard, the water really has to find a very tough way to get to the particle which is unhydrated and react with it. It may not be practically possible also. Question is heat of hydration more than strength? Okay, so question is heat of hydration related to strength? As I said earlier, yes, the total heat is related to the strength development. The higher the total heat, the higher the strength of your concrete. Crack repairs I have already talked about. Apart from water, what other solvent can be used to prepare concrete? Please remember, water is not a solvent in this case. It is only bringing the cement particles into solution in the early stages. It is not completely dissolving them. It is only making them more reactive at the surface. That is all. It is not really completely dissolving the cement. Okay, only the surface particles of C3S are dissolving and leading to the formation of CSH, and then you have the inner CSH formation. There is no dissolution that is happening beyond that period of early hydration. Okay, so there is no other solvent which can be used instead of water. Water is essential for cement hydration because only water reacts with the cement. I think I've answered all the questions here unless there are new questions that have popped up. Okay. What is self-healing concrete? Okay, that's a question raised. Self-healing concrete, of course, healing is related to the fact that concrete is able to actually close its cracks after they appear. So after the cracking appears in concrete, if the cracks close by themselves, it's called self-healing. Now what would cause cracks to close by themselves? One thing is, first condition is the crack is not very large, okay, it's not grown to a very large level. So crack is still small. What factors can contribute to closure of this crack? Some deposition of products that happens within the crack. Okay, sometimes you might have seen some literature related to bacterial growth of calcite within cracks. Okay, that's one way in which you can fill up cracks. The other way in which these cracks can self-heal is by a continued hydration of unhydrated cement. If you are continuously providing water, you will still cause the cement to hydrate, and that hydration product may actually fill up the cracks. That's one way to actually do self-healing. The other way to do self-healing is to provide fibers in the concrete. When you have fibers in the system, the cracks which are starting to grow will be controlled by the fiber and will not grow too much. Okay, so you have that effect in self-healing concrete. What is total heat evolution? As I said earlier, total heat evolution is the total amount of heat that you are evolving in the system, not the rate, total heat. So supposing I am reacting cement with water and I keep removing the heat and measuring it, that's my total heat that is actually evolved in the system. What is the significance of CSH gel? Now, of course, there is nothing more significant in cement chemistry than CSH, because CSH is the ultimate binding product that forms in your cement paste. Without CSH, there is no binding capacity of your cement. CSH is the primary binding phase, and that is why it is present in the largest amount as a hydration product. That is why your cement chemistry is such that CSH forms in the largest volume, and that is the compound which is responsible for actually binding your aggregates together and giving the strength to your concrete. Okay, I am not saying the other hydration compounds don't provide strength. They are still solid products that are filling up the volume and providing strength, but CSH is the one that is actually binding and creating this bound product which relates to the high strength that is obtained in cement. Okay, there's one more question is, okay, now this of course is related again to self-healing concrete. Is the transition zone in self-healing concrete in a continuous change? Now please remember, again it depends on the mechanism that you're providing for the self-healing process. Is your self-healing process happening through continued moisture, that means hydration? In that case, of course, the transition zone is going to change. Okay, so transition zone is the zone of bonding between the paste and aggregate. Okay, to those of you who have not heard this term before, it's the zone of bonding between paste and aggregate. It will change if you have continuous curing, okay, and if you have the presence of any bacterial deposition of calcite, that may also happen inside the transition zone. That I am not aware of very clearly, but maybe in that case also you may have a transition or change in the transition zone. Is there any effect of Bogue's compound on CSH gel? Now please remember, Bogue's compound, that is C3S and C2S, they are the ones which are responsible for producing CSH in the first place. Okay, CSH is formed because of the hydration of C3S and C2S with water. Okay, so they are obviously responsible for the production of CSH. What is the structure of the hydrated cement? Now that's something I'll show you a little bit later, so that you can see how these compounds appear under the microscope. You can see the appearance of ettringite, you can see the appearance of calcium silicate hydrate, and then try to understand how the structure of CSH is finally responsible for the binding as well as responsible for other issues like shrinkage, for instance. We'll talk about that in the forthcoming slides. Again, in the chat window, there's a question: if we add fly ash to the cement, will it reduce the heat or not? Of course, it will reduce the heat. Okay, when you are reducing cement content and putting fly ash instead of it, you are obviously reducing the rate at which your reaction happens, so you are going to be reducing the heat that is given out by the concrete. Presentation itself now, and we'll try to cover up. Alright, so before we do that, let's try and understand what is it that governs the speed at which cement reacts. Okay, how is the rate of reaction affected by the composition of the cement and by other external parameters. Okay. So if you look at cement hydration, we can divide that into 3 stages. The first one is the rate of dissolution of the involved phases at very early stages. I told you that as soon as the particles come in contact with water, the surface atoms of these particles start dissolving out and create the hydration product, right. So that in the early stages, the rate at which cement particles are dissolving is very crucial. So rate of dissolution is governing the rate of the cement hydration at early stages. What about later? What happens later? After that, as your cement hydrates and as the hydration products develop, it's the rate at which you can deposit these hydration products, which are either crystalline or semi-crystalline, the rate at which these are depositing. In typical crystal growth terms, we call it nucleation, rate of nucleation and crystal growth of the hydrates. Okay. Now please remember, now once you start forming this hydrated structure, the water has to come through this hydrated structure to the point where you have unhydrated cement and react with it to form the other hydration product. So the last stage of cement hydration is dependent on the rate at which water will diffuse through the hydrated layers to reach the particles that are not hydrated still. Okay. So you have rate of dissolution at the early stages, the rate of nucleation of the hydration products, and finally the rate at which water will diffuse through these layers to reach the unhydrated cement to continue the hydration. Okay. So these are the 3 factors which will control the rate at which cement hydrates. Now let us look at the parameters that will affect hydration as a result of this. First of all, obviously the phase composition of the cement. I already told you that the products that react or the compounds that react fastest are C3A and C3S. So the higher the C3A and C3S content in your system, the higher will be the rate of your reaction, or the higher will be the rate of strength development. Okay, that is why when you buy modern cements, you have very high levels of C3A and C3S content. The second is the amount and form of gypsum in the cement. I told you earlier, in the ball milling process, when the gypsum is added to the cement, because of the heat produced there, you can convert part of the gypsum into hemihydrate or anhydrite also. Okay, the rate at which gypsum reacts with C3A determines the rate at which you form ettringite. So if your gypsum is more reactive, that means if you have hemihydrate or anhydrite in the system, you will form ettringite much faster. That is all. Okay. So because of that, the form of gypsum and the amount of gypsum in the cement is important, because your early setting process is going to depend on that. Fineness of the cement. Now the finer the cement, the higher the surface area, so you have more available surface, so your dissolution rate is also going to be higher when you have finer cement present in your system. Okay. So higher the fineness, the higher will be the rate of the reaction. Water cement ratio of the mix. Now I told you already about the rate of reaction with respect to water cement ratio. At low water cement ratio, your rate of reaction is much faster, but nevertheless at high water cement ratio, your water content is so high that your hydration may proceed for a very long time, because you have a lot of water available in the system. Curing condition, of course, if you have very drying condition, right, you will not have any water present to hydrate the cement, it will start drying out. So that is why we need to provide curing to ensure that water has the chance to react with the cement to produce the hydrated skeleton, which is responsible for low porosity and permeability in the system. Okay. Hydration temperature. So when you increase the temperature, you increase the rate of hydration. Many of you must have heard of steam curing or heat curing, that is commonly done in precasting applications. They take concrete and put inside a heating chamber or steam chamber, which produces steam at a high temperature, and that high temperature actually heats up your concrete and increases the rate at which the reaction happens. Okay. So if you go back to the previous slide, temperature is one thing that is probably going to affect all these 3 things. It is going to affect the rate at which dissolution happens. Dissolution will be faster in the presence of high temperature. The rate of nucleation and crystal growth will increase, and the rate of diffusion of water also will increase when you increase the temperature. Okay. So again, temperature affects the rate of reaction the greatest. And finally, the presence of chemical admixtures. For example, if you have set controlling admixtures like accelerators or retarders, these can affect the rate at which the dissolution of the cement compounds happens at very early stages. Okay, that's why you produce the setting increase or decrease when you have either a retarder or an accelerator in the process. Okay, so these are the factors that affect the rate at which your cement hydrates or the rate at which it reacts with the water. Now I told you earlier that cement has these highly soluble alkalis, sodium and potassium oxide, right. I told you that these are often present on the surface of the clinker grains in the form of alkali sulfates. As soon as these grains come in contact with water, these alkalis are released into the water. Okay, when you have alkalis released into the water, this is actually just showing you how your water inside the concrete changes with time. So your potassium concentration and the sodium concentration increase continuously and then become saturated, because that is the point at which you have released all the alkalis that were present from your cement. So now you have your sodium and potassium which are present in very high concentrations inside cement paste after about 7 days. Now what happens to the negative ions? So since there is a positive ionic concentration, potassium and sodium, you also need to have a negative ionic concentration maintained. So in this case the negative concentration is maintained by hydroxyl OH minus. Where is OH minus coming from? It is coming from your calcium hydroxide, CaOH twice. So you have your calcium also coming here. See here, this is your calcium. The concentration of calcium, which is very high in the beginning, is not very high in the end, but it is there to some extent because it needs to balance your, it needs to provide your hydroxyl ion concentration in the system. Sulfate, in the beginning it is high because your sulfate phases are dissolving, but then as sulfate gets converted to ettringite and monosulfate, the sulfate keeps getting consumed and becomes almost zero in the system. So if you take a concrete that is hardened and you are simply pressing the hell out of it, if you really press out all the water from inside the concrete, you will find that if you do an ionic analysis of the water, you will find that it only has sodium, potassium and hydroxyl ions, Na plus, A plus and OH minus. Okay, and your pH of the system is going to be as high as 12.5 or 13, and that high pH is maintained because of this very high alkali oxide concentration that is present inside your pore solution. Okay, so your calcium hydroxide, your alkalis are both responsible for producing a very high pH in your cementitious system. So now let us look at hydrated cement paste. Now this is the most important fact as it relates very well to how your concrete structure finally looks like and how concrete finally behaves when it is exposed to different sorts of loading or exposed to different sorts of environmental conditions. Okay, so hydrated cement paste is composed of capillary porosity and the hydration products. Okay, so you have porosity in the system because when cement hydrates and reacts with water, there is no way you are going to fill up the entire volume with solid. So there will be a lot of porosity that is still vacant or zones that are not occupied by solid present in the system, that is called capillary porosity. Okay, now apart from capillary porosity, the solid hydration product itself like CSH, which we called earlier as gel, it's also got some porosity within its structure and that is called gel pores. Okay, you have capillary pores and then you have gel pores. Okay, gel pores are what are within the structure of your CSH itself. The hydrated cement paste is composed of hydrated products like CSH, calcium hydroxide, ettringite, monosulfate, etc. Okay. Now again I told you earlier that calcium hydroxide, ettringite and monosulfate are very well crystallized materials, so you do not really worry about any porosity inside them, but CSH is semi crystalline and it has got a lot of porosity inside, and that is what is responsible for the gel porosity, gel pores. Okay. So according to Powers, who was also one of the premier scientists as far as cement chemistry is concerned, 1/3 of the pore space is gel pores and the remaining 2/3 of the pore space is capillary pores. Now you will obviously realize that when we are talking about capillary pores, they are going to be of a much larger size as opposed to gel pores which are very small. So capillary pores are present outside the hydrated product, gel pores are present within the hydrated product, so they are of much smaller size as opposed to capillary pores. Some microscopic images to help you understand the structure of the hydrated cement. On the left side here I am showing you a picture from a scanning electron microscope image of a cement paste that has been fractured. You just fracture the cement paste and observe it under the microscope. you can actually see the fibrous structure of your CSH. You see all these particles are of CSH. You don't really see any well defined crystalline structure from this phase. Okay, you see a fibrous structure. Now this is again a picture from a microscopic image, but in this case the specimen has actually been polished to reveal the contrast because of the brightness of the phases. So you see again this is quite similar to the picture that we saw earlier, which showed the inner and outer CSH. So here there is a large void here and you see the aggregate particles. You also see a very bright rim of white just around the aggregate, and you also see some white deposits inside the porosity here or inside the void here. That white deposit is that of calcium hydroxide, and the grey area surrounding the particles is that of calcium silicate hydrate. Now this picture on the left is actually from a mortar in which there is only C3S, okay, there is no cement, there is only C3S. So as you can rightly guess, when the C3S react with water, it is only going to produce CSH and calcium hydroxide. So I will show you where these are. So you see here the bright white phases are the remaining parts of the unhydrated C3S particles. So bright white is the unhydrated C3S. Just surrounding the bright white, you see this light grey regions, that is your dense inner CSH. As you move away, there is a slight darker region here. The darker region is basically your outer CSH, and then you have other white phases that are here, and here these are white phases. You see some white phases around the aggregate particles also. Those white phases are basically your calcium hydroxide. Okay, in this case you do not expect any ettringite or monosulfate because it is only C3S that we are looking at here. Okay, so that is clearly showing you how these hydration products are actually distributed within the system. If you look at the concrete image under the microscope, you see several large aggregate, smaller aggregate, and the zones in between occupied by cement paste. Now the thing is, if you look at the overall picture of concrete, about 80% of your image seems to be only aggregate, only 20% of the volume is looking like cement paste, and that is exactly what you have in normal concrete, that only 20% of your normal concrete is actually cement paste, remaining is just aggregate. So truly speaking, the zone that is between your paste and aggregate, which we otherwise call as interfacial transition zone, is possibly there throughout your cement paste itself in this case, because there is so much little of cement paste that is actually available in this picture. But still, if you look very closely in the cement paste itself, you can actually see the porosity of the cement paste, which is the black spots present within the cement paste itself. Okay. Now while we are producing concrete, we use a water content which is typically large enough not just to react with the cement, but also to produce some initial workability, right. We want some workability, so we can work with the concrete and produce the required form or shape that we are trying to fill up. Now what happens to this excess water? Where does it go? So water is held in concrete in different forms, okay. Within the cement paste itself, it is held in different forms, okay. The first one is capillary water, okay, which is present in voids which are larger than 50 angstroms, okay. Angstrom, please remember, is 10 power minus 10 meter. So in other words, 50 angstroms is nothing but 5 nanometer, okay. So if you have voids and pores which are larger than 5 nanometer, those are called capillary pores, okay. So capillary pores, as I told you earlier, are outside the hydrated product, which are present in the bulk of your system, okay. So again, you can define capillary pores into two categories, one which are fairly large, okay, which are free water, which contain free water, which are held in large pores. So when you remove this free water which is present in large pores, it does not cause much shrinkage in your concrete. But then water which is held by capillary pressure or capillary tension in small pores, if you try to remove that water, it causes a lot of shrinkage. Why is that? Again, you remember your basic physics, when you have very thin capillaries, you have a great rise of water inside the capillaries because the capillary pressure is high. When you have large capillaries, water does not rise inside very much because you have very low capillary pressure. Similarly, if you have a water filled capillary which is very large, if you try to remove water from there, it will not produce much capillary pressure, so your shrinkage strain will be low. But if you have a very thin capillary pore and you are trying to dry the water out, it is going to produce extremely high capillary pressures and lead to very high levels of shrinkage. So Why is this important? To understand, this is important because water within cement paste can be present in different sized porosity. When it's present in very large pores, you're not really bothered about shrinkage, but when it's present in very small pores, the shrinkage can be really significant. So capillary water again is either free water or the water held by capillary tension, which can produce shrinkage. So it's needless to add that when you have the gel pores and the gel pores have water inside them, it can obviously be a very high level of shrinkage that can be associated with that. Okay, so gel pore water is usually in two forms. You have adsorbed water or interlayer water. Again, when I tell you the structure of CSH, this will become much clearer. So adsorbed water is water that is physically adsorbed on the surface of the CSH particles, and interlayer water is the water that is trapped between layers of CSH. So when you are trying to dry the concrete and pull out this water, it's going to cause a major collapse of the structure, which leads to a very high level of shrinkage in the system. And finally, you have bound water. Bound water is what is bound in the structure of the hydration products, like CSH. I said that one of the formulas for CSH is C3H2H3. So that 3H2O is the water that is bound to the CSH structure. Then you have calcium hydroxide, there is bound water in that. Ettringite has bound water, monosulfate has bound water. Okay, that water cannot be removed by drying. You have to actually heat beyond 100 and almost up to 1000 degrees to completely remove that water that is present in the bound form in the CSH and other hydration products. So again, this is actually giving you the phase composition data for a typical ordinary Portland cement paste made with a water cement ratio of 0.45. Okay, this table you can go through on your own. So volume percentage is given at the time of mixing and in a mature paste itself. So what I wanted to draw your attention to is the amount of CSH that is there in the system. The CSH which is solid or inner CSH is 29%. The CSH with gel pores, that means the outer CSH, is 50% nearly in the system. So look at the extent of CSH that is there in the system. Calcium hydroxide is about 14%, your ettringite is around 6.8, monosulfate is about 15. That means ettringite is still getting converted to monosulfate. And if you look at the bottom here, the gel porosity is about 21% and the capillary porosity is about 10% in the system. Okay, so how the system has evolved from when it was mixed to after it's become a mature paste. So your porosity also evolves as your cement continues to hydrate, more and more of porosity shifts from capillary pores to gel pores. So that's what is being shown in this case. So now let's look at the structure of the hydration products itself and see what level of detail we can see under the microscope. So first and foremost, we look at the structure of paste at very early ages. So this picture is actually showing you cement paste which is at very early ages. Okay, it's a 7-day-old hardened cement paste. You can see here on this side that this cement particle is gotten covered with this fiber-like appearance of the CSH. Okay, this is CSH, and you also have several needles that are being shown here. Those needles are those of ettringite. Needles are of ettringite, and there are some plates here. You see some plate-like structures. Those plates are of monosulfate. Okay, and you have a very large crystal, a darker looking crystal on the side here. That dark looking large crystal is actually that of calcium hydroxide. So this gives you a brief picture of how these phases are. CSH is extremely fibrous and looks like a material which has a very high surface area. Calcium hydroxide is present as large crystals, ettringite needle form, and monosulfate in plate-like form. So these are the different forms that you actually see are cement hydration products in. Some more closer pictures of CSH, you can very clearly see the loosely crystalline nature. You don't really have a very clear-cut crystalline shape or size to CSH. It's got a loosely crystalline fibrous sort of an appearance, which seems to suggest that CSH has a very high surface area. This is again CSH that is formed on a particle of C3S. Again, very high resolution imaging has been used in this case. You can see many such images from different websites. Actually, I picked this one up from cementlab.com, which is a very useful website to look at microscopic images of cement particles. So the very fact that CSH looks very fibrous and suggests that it's got a very high surface area has led researchers to investigate the structure of CSH itself. one of the most popular models that seem to be accepted as far as structure of CSH is concerned is this Feldman-Sereda model. Okay. Now I told you earlier that the other hydrated products like ettringite, ettringite, monosulfate, calcium hydroxide, these are well defined crystals and they don't really have any porosity inside, whereas CSH has porosity inside its structure. So how do we explain the structure and how do we account for the very high surface area of the CSH? So Feldman and Sereda, who are again two scientists who proposed this model, state that CSH is present in sheets of calcium silicate. So you see here the solid lines are actually sheets of calcium silicate hydrate, CSH, okay, calcium silicate layers, okay. In between the sheets you have these things called marked as X, okay. You have the water which is marked as X, the water between very small micropores between calcium silicate layers. So that's the interlayer water that has been marked as X there, okay. And then you have these O's, okay. The O is basically molecules of water that are adsorbed onto the sheets of CSH. The O is basically water molecules in micropores or physically adsorbed on the external surfaces of CSH. So you can imagine that when you are trying to draw out this water by drying, the CSH sheets will start collapsing or merging into each other. So there is going to be a very large volumetric shrinkage. On the other hand, this CSH agglomerate particles have a large gap in between here, and that large gap is basically your capillary pore, which is marked as C, which is a bulk water. When you remove that bulk water from the capillary pores, you are not really going to cause much drying unless the capillary pores are very small in size. When do they become very small in size? When you reduce the water to cement ratio in the system. When the concrete becomes stronger and stronger, you are reducing water to cement ratio in the system. Capillary porosity also keeps reducing much more. So it almost becomes impossible to actually dry out that water very easily under normal drying conditions, which is why when we have very high strength concrete, we are not really worried about drying shrinkage anymore, but we are worried more about autogenous shrinkage. Anyway, we are not talking about that here. So I just wanted to show you the structure of CSH. Basically, it's the most widely accepted one, which presents calcium silicate in the form of sheets, which has water trapped between layers as well as water adsorbed on the surface, and then you have capillary porosity, which also contains some water inside. So again, if you look at that model of CSH from Feldman-Sereda, it seems to suggest again very high surface area for the CSH. Indeed, surface area has been measured for CSH through a number of different types of experiments, and the values reported are of the order of 200,000 square meters per kilogram. Please remember, your cement itself is only around 300 square meters per kilogram. So we are producing a material that is completely different from cement, which is why understanding cement chemistry is important, because it helps us understand why concrete behaves in a manner which we don't expect the cement itself to contribute to. Okay, that's because of CSH. Now interestingly, when you actually do heat curing of the CSH of the concrete, when you do heat curing or steam curing, the CSH surface area reduces to about 7,000 square meters per kilogram. That means you are producing a much more coarser material. Okay, indeed, when you try to test heat cured concretes as opposed to normally cured concretes, you will find that the long term strengths of heat cured concretes are lower than the long term strength and durability of normal concrete. So heat curing, although it produces high early strength, does not behave as well as normal concrete in the long term. So you have that problem definitely with the use of heat curing. Okay, so heat curing leads to a higher or lower surface area of your CSH and higher macro porosity within the CSH. Okay, so again, CSH occupies 50 to 65% of your paste. It's got high covalent and ionic and van der Waals forces that are keeping it very cohesive, and that's basically responsible for the binding nature of your cement paste itself. The other particles are, as I said earlier, filling up a large volume because of their crystalline shapes. Calcium hydroxide, very well defined hexagonal crystals. The van der Waals forces are low, surface area is very low, because you can imagine when you have a well defined crystal, it's got to have a low surface area. You have here, these are hexagonal crystals of calcium hydroxide, and these occupy a volume of about 20 to 25% inside ordinary cement paste. Now ettringite and monosulfate, as I told you, are produced because of the reaction of C3A and C4AF with gypsum and water, and you have structure of ettringite best represented by the form of these needles here. Okay. Now again, there is a lot more to understand as far as ettringite is concerned. It forms in different types of shapes and sizes depending upon the conditions that are prevalent within your concrete. Some forms of ettringite are expansive, some are not expansive. The needle form is especially expansive, and that is what we are worried about. When it forms in hardened concrete, it can lead to expansion and cracking of the concrete. Whereas monosulfate, which is a stable form of calcium sulfoaluminate, please remember, in ordinary Portland cement paste, ettringite slowly converts to monosulfate, and monosulfate remains stable over the long period of time, that the plate like shapes are basically those of monosulfate. Now a very important concept is the understanding of the sizes of pores and voids that are formed inside the concrete. Okay. I will go with the highest order and then go for the smallest pores and voids that are available inside the concrete. At the highest extent, on the right hand side of this image, you have what is called an entrapped air void. Now why do you produce an entrapped air void? It is because after you mix the concrete and compact it, there is no way that you can release all the air from inside. Okay, compaction means your concrete fills up all the available space properly, but there are certain gaps which are still going to be remaining. Most often these gaps exist at the interface between paste and aggregate, because your paste is not properly encapsulating the aggregate there. So that is called an entrapped air void, and we are looking at sizes of several millimeters in that case. You see here, this is 1 millimeter to about 5 millimeter sizes we can expect in your entrapped air voids. Now you might have heard that in certain conditions, such as in freezing conditions, we sometimes use air entraining admixtures. These air entraining admixtures create very small micro air bubbles, which are actually distributed in this size range. You have from several tens of micrometers to about 1 millimeter size is your small air bubbles that are entrained in the system. Okay, these air bubbles are entrained purposefully from the point of improving the freezing and thawing resistance of your concrete. Now these are at a completely different scale as opposed to your voids and pores which are present within the cement paste itself. If you look at the capillary voids inside the cement paste, they occupy a size all the way from 10 nanometer, okay, 10 nanometers. Okay. I earlier said 5 nanometers, but more often people say 10 nanometers, all the way up to about 1 micrometer. So 10 nanometers to 1 micrometer is the range of sizes for capillary voids. And if you look at CSH particles on a large scale, agglomeration of CSH particles is about 1 nanometer in 1 micrometer in size, and hexagonal crystals of calcium hydroxide are of the same size of about 1 micrometer. If you go to the interparticle spacing between CSH sheets, remember that is where you have your interlayer water inside. Okay, that we are talking about very few nanometers. We are talking about less than 5 nanometers. So you can imagine if you are trying to pull out water from that size porosity, it's going to cause a major volumetric shrinkage. Okay, so it's very important to pay attention to this, because this governs the range of sizes of pores and voids that you might find in concrete and within cement paste more particularly. So entrained air and entrapped air is in concrete, and all these other voids that I have shown you, or the sizes of the particles, are within the cement paste itself. This picture again gives you a more better description of the different types of capillary and gel pores that are seen in your picture, and how much is the size of the ITZ. Again, all these are from research data, but they are presenting very useful information as to what sizes of porosities are typically observed in cement paste phases, and that is very important from the perspective of understanding how will the strength and durability of concrete be affected when you have different sized pores present in the concrete. Okay. So I want to end my talk here so that we can take questions to finish up this lecture, but I wanted to re-emphasize this point that ultimately when you look at concrete behavior, be it strength development, be it response of the concrete to the environment, be it drying shrinkage, creep, all those are actually associated with the way that cement forms cement paste, or it's associated with cement chemistry, because ultimately cement chemistry is what is responsible for producing the different hydrated phases. What remains stable inside the cementitious system governs how well cement or concrete responds to its environment. CSH, again, as I said earlier, it's the primary binding component. It's responsible for strength development of your concrete, but CSH is also responsible for creep and shrinkage inside the concrete. Okay, so you have to understand the nature of CSH, the characteristics of CSH, and how you can actually produce concrete which has well controlled properties as far as not just strength and durability are concerned, but also dimensional stability is concerned. And all these factors are actually affected by cement chemistry. Okay, so at this stage we will stop the lecture and we will take up questions so that we can finish up with a much clearer understanding of cement chemistry. Okay, so the floor is now open for questions. Here we have one question. This question is on what can be the effect of natural fibers on the kinetics of cement composite material. Now, cement hydration itself, we are talking about the early stages of cement hydration and the reaction of cement with water. Now, when you add a fiber, we are only looking at the behavior of concrete in the long term. For example, what is its fracture toughness, what is the response to the loading, because fibers are effective only after we have some level of stress in the concrete. So, fibers help to bridge cracks within the concrete and prevent the cracks from growing, and this helps in improving the post peak load carrying capacity of the concrete. So, the fibers themselves would not really have any impact on the cement hydration. Natural fibers sometimes may actually degrade in the cementitious environment. So, you need to be careful because of the high pH of cement, you may have a degradation of the natural fibers. So, that may affect your fiber performance itself, but as far as cement chemistry is concerned, I do not think it is going to be affected by the presence of the fiber. Is there any difference in the CSH developed due to C2S and C3S? No, there is no difference in the CSH that is developed because of C2S and C3S. In both cases, you form the same fibrous crystalline, semi-crystalline material. But as I was telling you, in modern cement, the main contribution of CSH is only coming from C3S, because C2S rarely has a chance to react, because by the time the C2S is ready to react, the hydrated structure has already got so developed that it is difficult for water to actually start reacting with C2S. So, in most cases C2S would not have reacted much, but nevertheless C3S and C2S will end up producing similar calcium silicate hydrate. However, when you have a pozzolanic reaction, that of a reactive silica with calcium hydroxide, the pozzolanic CSH that you produce is rather different compared to the cementitious CSH. The pozzolanic CSH typically has a lower calcium to silica ratio, okay, as opposed to cement related CSH. If there are no further questions, I'd just like to show you a small schematic on the board to help you understand how the filling up of the porosity happens much better in the case of a low water to cement ratio system, okay, and that will help you understand that in low water cement ratio systems, even if I do not have very high levels of hydration, I can still achieve very good strength and durability in the system, okay, although I do not have 100% hydration. So, I will show you a schematic just to help you rethink your understanding of how you produce high strength or high performance concrete. Now, let us assume this is my volume that I need to fill up with my mixture of cement and water. So, in a high water cement ratio system, I have lot of water present in the cement, okay. I have a lot of water present along with the cement. So, if my cement is hydrating on the surface, it starts creating this hydrated surface. Okay, now it will take a very long time before these hydrated parts start overlapping, okay. I want the hydrated parts to start overlapping because only then my structure will fill up and I will get setting and hardening. On the other hand, if I have a low water cement ratio system, that means I have more cement particles in the volume of the water, a lot more cement particles. Okay, in this case what happens? Now if I start hydrating on the surface, even at very early stages of hydration, my hydrated phases start overlapping. When I get an overlap of hydrated phases, I start forming my intact structure much earlier as opposed to the system which has lot more water. So in a low water cement ratio system, not only am I producing setting and strength gain happening much faster, but my overall filling up of the available porosity is much better in the case of the low water cement ratio system. Now one thing you should also understand is that when I do not have sufficient water in the system, my cement is also not going to get completely hydrated, but that is not really a problem. The remaining part of the cement which is not hydrated is simply filling up the space and working as a filler. All I need is this hydrated structure network to form, and that fills up or that produces a necessary degree of binding to give me my required strength and durability. So this is a very crucial concept for you to understand, because when you have more cement particles in a given volume, you are able to create the bridges of hydration products much faster, as a result of which you get much better rate of strength development and overall much better strength and durability in the long term. Okay, so low water to cement ratio produces stronger and durable concrete, even though the cement does not hydrate as much as in the high water cement ratio system. Okay, now that may be contradictory to you, but if you think about it very carefully, that's what it will end up doing. So less porosity, less pore connectivity, much better strength and durability for low water cement ratio. The question is, due to climate changes, will we develop porous or air voids in concrete? I am not sure how climate change would develop porosity or air voids in concrete. Uh, that is mostly how we are actually producing and mixing the concrete and compacting it. Climate change cannot do that. Uh, do voids affect the heat of hydration? Now voids will not affect heat of hydration. Heat of hydration is primarily dependent on how your cement reacts with water and what the reactivity of the cement itself is. However, if you have more water in the system, like I showed you in this diagram earlier, more water means more voids. So if you are having more voids in the system, that means you have started off with more water, and if you have more water, your heat of hydration will be lower. Okay. So that way they are probably related, but voids themselves don't really affect heat of hydration. Whether there is any special material or compound to increase the strength of concrete. Of course, there are many different compounds that can increase the strength of concrete. One way to do that is to replace cement by supplementary cementing materials, by using very fine fillers, for instance. Okay, these are all different ways of increasing strength of concrete. When you use silica fume, for instance, you can increase the strength of concrete and so on. Rate of diffusion of water is formed when dissolved ions are formed. How? I am not very sure what is being asked here, but see, please remember cement hydration, I broke it into three different stages. One was, as soon as the cement particles come in contact with water, the surface atoms start dissolving. Okay, then the hydrates start forming and start growing, and when the structure grows and you have a hydrated network that forms, the water that is going to react with the unreacted particles now has to come through this hydrated layer by diffusion, and that is what is the relationship between dissolution of the cement compound in the early stages and diffusion of water through the hydrated network to hydrate the unreacted particles. Okay, so there is, I presume that is what you wanted to ask in this question, but that is what I tried to answer. What happens to CSH when the concrete is subjected to high temperatures during a fire accident? It's a good question. Now, concrete has cement paste has different phases. You have ettringite, you have monosulfate, you have calcium hydroxide, and then you have CSH. So in a fire accident, what will happen is, first of all, the free water from CSH will get removed, and the water that is not bound to the CSH will first get removed. Okay, then you will have a removal of the bound water from your ettringite and possibly a little bit from the CSH also. As you increase your temperature further, you will start removing the water from the monosulfate as well as from your calcium hydroxide phases. Now the main change or volume decrease in the concrete will actually happen when the calcium hydroxide that is present in your cement paste gets decomposed. That means it loses its water. So that happens at around 500 degrees Celsius, 450 to 500 degrees Celsius. So your major loss of the concrete strength actually starts happening around that temperature, 300 to 400 degrees, and mainly the major loss will happen right after the calcium hydroxide completely decomposes. But the overall bound water loss can happen up to about 6 to 700 degrees Celsius. Okay, so that will be the different stages of loss of water from your concrete. Okay, having said that, the change in phases in the concrete will be happening at different temperatures during a fire. I should also add that concrete has a much better fire resistance as opposed to steel. So in a reinforced concrete structure, the concrete cover that is on top of the steel will actually protect the steel for a long period of time before your structure becomes debilitated. So the cover concrete is really responsible for protecting your structure until you do the firefighting. So in most of the cases, if you look at a fire damaged concrete site, the damaged or spoiled concrete is because the steel starts deflecting at at temperatures which are higher than about 250 300. When the modulus of elasticity of steel reduces, you have deflection of the steel that pushes out the concrete, and that's what is mostly responsible for concrete failures that you actually see in fire damaged buildings. The concrete itself will get damaged to a large degree only after about 500-600 degrees Celsius. Okay, so it actually helps in protecting the steel from getting damaged at a very early stage. Okay, so your reinforced concrete structure, because of the concrete cover, can really do a very good job in fire resistance as opposed to a steel structure. Role of adsorption in hydration of cement. Now, we don't really have the process of adsorption taking place during hydration, but adsorbed water is finally present on the surface of the hydrated CSH gel, right. So adsorption itself is not responsible for hydration, but adsorbed water finally is there in the CSH. So I hope you understand the distinction between the two. Adsorption is when you have molecules of water coming and attaching on the surface of the hydration products, and that happens in the final structure of the paste itself. Adsorption, however, is not a requirement for cement hydration to happen. Cement hydration happens first by dissolution, then by nucleation, and finally by diffusion of water. You still have a couple of minutes, so in case you have some pressing questions, please do ask right now. Or even if you have questions later, I have given you my email address earlier. I'll rewrite that address and also the website from which you can get more information, so that you can follow up with what content I have presented here and continue to learn whenever you want. Okay, my email address is manus@iitm.ac.in, and the website is http://www.theconcreteportal.com. So all this content that I've gone through in this series of 3 lectures is mostly available, along with several other pieces of information about concrete. As I already mentioned in my first lecture, this website is not intended to be a substitute for a textbook. It's only something that you can add on to the textbook. There's a lot of information here, from basic concrete fundamentals all the way to advanced topics in concrete technology, based on several research studies that have been performed here at IIT Madras. So the information will be very useful to you, not only from a understanding concrete viewpoint, but also from deciding what course of research you'd like to take for your masters and PhD sort of studies. Okay. All right. So if there are no further questions, I'd like to thank you all for joining us during these 3 sessions on cement production, composition, and chemistry. I hope the session was useful for most of you, and that you'll be able to understand cement and concrete behavior much better thanks to the inputs that you have in these 3 modules. So thank you all very much, and I wish you a very good semester ahead.